that being inside the box means we are outside the solid. And there's an important problem involved here, of course. It's part of the reason people don't believe in cold fusion. Characteristic momenta are many, they're like, 10 to the 9th electron volts per C, and they ignore interaction with the solid pretty much, because the characteristic scales for interaction with the solid are like 5 orders of magnitude different in length. Now, the point is, though, that the electromagnetic interaction, if these two Ds could be correlated with each other on length scales that are far apart, and in fact, that's what's known, this was actually coupled to the solid and coupled to a lot of things. And that's totally ignored when if you have a situation, and you do, and I'll show you where this correlation does occur, you can get significant kind of coherent effects. And the point is, okay, here I've gone back, and before I put the helium-4 on the boundary here, and I keep it on the boundary here because in regular fusion, it doesn't occur very often, and the nuclear physicists have largely ignored it. Part of the reason there is there's not much literature about helium GD going to helium-4 plus gamma, but there is a lot of information about the reverse reaction. It's been studied to death. And through microscopic reversibility of quantum mechanics, one knows that the underlying wave functions and the behavior of these things has to be the same in this reaction as in the reverse reaction. And so the point is, that what goes on here, these two things have to behave like bosons far away from the reaction, very far away. And they have no spin, and they form like what is like a kind of molecule at far distances in the sense that they have an orbital, well-defined orbital angular momentum equal to 2. So here are some facts. The nuclear, what I just said, the nuclear transition in the forward direction is from a spin 0 type configuration. I'm just showing the matter distribution here. It should be 0s and a 0 down here to an orbital angle, to a total angular momentum equal to 2, and it's got spin 0, and it's an orbital, totally orbital. It involves no direct magnetic coupling. Theory and experiment explain it. They explain it quite well. It does not involve vacuum polarization. It is dynamical. It is not explained by gamma theory. It's based on a static problem. It is not short range. The final state Ds must obey boson exchange symmetry far from the reaction. It does not occur in fusion because of this electromagnetic effect. It involves long distance coupling that includes the relationship between spins and particle indistinguishability. In other words, the two Ds effectively must be able to exchange places on all time scales, so you don't actually know which one is which. And for that reason, that introduces a notion, a kind of spooky action at a distance associated with coherence that we all know very well. Now, okay. Now, so what happened to the gamma ray? Now this is shifting gears a little bit. It's getting into an important point. I've shown this video before, but this is a prelude to how you get this kind of wave-like behavior properties of solids in solid-state physics. And this is something that's not studied very well. But the point is, electromagnetic radiation penetrates to all length scales. Momentum does not equal mass times velocity. That's a common misconception. Momentum, in the sense that's used quantum mechanically, is proportional to the current. And the current involves the electromagnetic field. It involves the vector potential. And you can actually have limits where you can get very large momentum or a sudden shift in momentum, a sudden shift in vector potential, and have a small current. And this is the origin of coherent effects such as current superconductivity. Basically what happens is you can have regions where the momentum is going to 0, as in a Bose-Einstein condensate, but you can really have, but because this is 0, you have the current proportional to A. And in fact, that's an interesting example of what is called broken gauge symmetry, and the process can be one in which the entire solid moves coherently. And that is, every entity in the solid requires a common phase. And this is the basis, actually, of wave-like properties in solids, known from solid-state physics. So the point is, all of this is really well known in solids. And it is known that these kinds of coherent effects can even occur at 0 momentum. point is that many particles, static or wave-like reactions, can break gauge symmetry. That's what I was just referring to. That's when lots of particles acquire a common phase. A well-known example, actually, is the problem if you have photons that are absorbed, transmitted and absorbed, and never leave the solid. You have situations involving transverse kinds of modes that are allowed by electrodynamics, where the coupling can involve many wave-like kinds of configurations in which everything in here is basically microscopically reversible, in quotes, and you get breaking of this kind of symmetry with the formation of dipole layers. This is actually the basis of Bloch's theory. A solid, any ordered solid at a temperature equal to 0 is a superconductor, and that's the basis of this kind of argument. When photons are emitted and absorbed by many charges that behave as if they are static, photons cease to be photons. That's the basic point. Gauge symmetry, as soon as this kind of effect never occurs, it occurs all the time. Stop. Gauge symmetry was something. What that refers to is the notion that in free space you can you can have particular relationships between the vector potential and that you can change it by adding a constant gradient. But you don't have to worry about that when you're dealing with solids because you're dealing with currents and things like that. So this occurs all the time. Gauge symmetry can be broken. Now, the point is, well, how does this relate? You can get situations in the limit of vanishing momentum, J and H in color, coherent. When this occurs, long-range interactions become possible in which a photon is shared at many locations. And what I've done here is I've shown the canonical example of a periodic density. Now, a density has a quality. This is it could be the current, either the current or the density. This is the representation of either of the field that you would get, the electromagnetic field. And you get the standard idea of photons is associated with the fact that the speed of light times 2 pi over the wavelength, which is k, is equal to 2 pi times the frequency. This is when this thing vanishes, you pick up the contributions that give rise to conventional light. In a situation where you get a photon entering a case where it's always absorbed, you can get these really eerie situations where it can couple coherently to the natural periods associated with the underlying structure, if there's some underlying structure. And so what can happen is a wave vector can actually be very small, but coupled to a very large frequency, so you can get a large amount of energy coupling. This is sort of the basic. This is a canonical representation of the kinds of processes that can go on in solids. So that effectively, you can view it in many ways. You can view it as if you try to hit the solid at an isolated location. Well, that's the other point. If a small amount of K goes to all the different points in the lattice, it actually becomes a reciprocal lattice vector. And what happens is all of that momentum is shared by many points at once. When it gets shared by many points at once, the solid as a whole can recoil. And my final view graph relates to a picture that can be used based upon this kind of model. What you have are regions. These are regions denoting the separation between deuterons, where it's of nuclear dimension. But you can require in these situations a very funny limit. The same matrix elements that apply in regular quantum mechanics can apply in these situations, except there are many different locations where it's a wave-like configuration where the momentum is 0, but the vector potential is not, and you can get coupling, and the entire solid can recoil. The mediators of this recoiling problem are ion band states, or could be. There are many generalizations. This is a particular limit. This is a low temperature limit. The whole framework actually adapts itself in logical ways to much more complicated things. And it actually does relate to a number of the things that Peter Hagelstein will talk about, the conventional sort of many-body physics. This is a low temperature kind of limit. All right. We have Peter Hagelstein. Oh, I'd like to make a comment. We initially screwed up his schedule, and technically he was only supposed to give one talk, but he gets to give 2, so it's great.
I've been interested in an experiment performed by colleague Kasaki at Tohoku University in Japan. What he did is, following the announcement of the cold fusion effect, and the controversies surrounding it. He studied low energy and mid-range energy.
So,
100, in this case, 100 kilovolt deuterons hit a titanium deuteride target, and he was looking to see what nuclear reactions came about. Now, at low energy, off the graph here are the normal DD fusion reaction products, including 3-MED protons and 1-MED neutrons, tritons, and helium-3. At high energy, up in the neighborhood of 15 MeV, he sees also protons, but these protons come about from secondary reactions where helium-3 that's produced hits deuteron and can make a fast proton. So that's this peak. He also saw something that hasn't been seen before, and that's this background here. This background is broad, and such a broad background ranging over lots of MEV is a signature of a possible three-body reaction, or three-body exit channel. Now, Kasagi thought about all the possible reaction mechanisms that the codes could generate. There might be possibilities. About the only one that turned out to fit the data for the protons. Similar effect was seen in the high energy alpha spectrum up to 6.5 MeV. It was the case of a single deuteron coming in and hitting two deuterons close together. So in this case, there would be a three-body incident channel. 6 particles or 6 nucleons altogether. The reaction exit channels are alpha particle, it being a three-body reaction, the energies of the reactants are spread, and the endpoint energies for the three-body exit channel from a DDD reaction is consistent with this data. And these experiments of Kasagi have been replicated by Kasagi, been replicated at 2 other Japanese laboratories, a Chinese laboratory. Last year they were replicated at the Naval Research Laboratory. I've been interested in this problem because I thought it was a very fundamental problem. The basic idea being is that if you interpret the Kasagi experiment as being a diagnostic on the occurrence of deuterons at close range, then the question becomes about how do they get to be in close range. Now, if you model fusion reactions in a vacuum, what was used initially was something called the resonating group method, created by Wheeler. The basic idea is you're doing your quantum mechanics with the total wave function. You do a superposition of the nuclear internal pieces of the wave function, like a wave function with deuteron, the internal coordinates is roughly exponential. And you have the channel separation factors, which tell how far apart the deuterons might be. To optimize the wave function, you can use the LENR, and you can use a variational method. You get what's called coupled channel equations. These coupled channel equations were used by physicists up until about the 1980s or so to describe DD reaction physics. Our matrix methods tend to be preferred in this day and age, and the formulation is closely related. I propose generalizing this to the lattice resonating group method. The basic idea is instead of having a two-body channel separation factor, replace it with a full many-body lattice wave function, where if you have two bodies going in or two bodies going out, the channel separation factors talked about their center of mass wave function. And so if you have many particles around and include the center of mass wave functions, it looks like a normal lattice wave function. The optimization of the lattice wave function can then be used in the same framework as resonating group theory from Wheeler. So you can actually do vacuum nuclear physics or lattice nuclear physics using the same formulation, but with vacuum physics being a subset of the lattice generalization here. Now, one consequence of the new model is that you can have phonon exchange during a nuclear reaction, during a fusion reaction. For example, normally it doesn't do anything. All first-order fusion reactions within this new model occur at the same reaction rates and have the same reaction energies and so forth, so that there's phonon. But if you exchange two phonons for a DD reaction, you can change the microscopic selection rules. Two phonons can contribute to an inverse of angular momentum, which can get you to a helium-4 phonon-induced reaction. Another thing that the model suggests is that you can have side-other-side reactions. For example, if you exchange phonons with a common phonon field, then quantum mechanically you can have a second-order reaction. The most interesting of such reactions is what I'll call a null reaction. The basic idea is that you have two deuterons going to helium-4 coupled to a phonon hub, and helium-4 going to two deuterons on the other side. This overall second-order reaction basically doesn't here and helium-4 here, and they just seem to switch places, so no energy is released. The theory modeling this is straightforward within the theory. You start out with an initial wave function that has basically deuteron pairs of helium-4 at different sites for A, B, and so forth. Then you get couple channel equations, and you can work with the couple channel equations. I've been looking into various approximations for the lattice wave function. One interesting one is one in which you make the total lattice wave function separated into local wave functions. The idea being is that except for the common phonon field, all of the physics is probably local physics. So local physics of site A, local physics of site B, and phonon mode that's extended over many sites. When you model things, you get coupled reactions. In the end, if you use second-order perturbation theory, you get coupled equations for the deuteron-deuteron channel. The basic idea is the deuteron-deuteron channel locally looks like a molecular problem inside of the lattice potential, very similar to what many people have analyzed. The extra terms here come from the fact that you can have two deuterons at another site going to helium-4, and having helium-4 at the site you're considering turn into two deuterons. So you get a source that's local. This source that's local, it looks complicated, but in essence the effect is simple. You can understand it in a simple one-dimensional case. If you take a one-dimensional potential well and you take a segmented potential well that's sort of an analog of a helium molecular state, you have a low potential, you have a higher potential, and the low potential here, the high potential here mimics the Coulomb repulsion. The zero mimics having a molecular state at some distance out near L. The exchange term that shows up is meant to mock up the physics of when helium-4 comes apart, the two deuterons are produced initially close together. And that basically means you've got a function here that's localized near the origin. If you use it as a delta function, you can solve this equation exactly. And when you solve it exactly, you get the ground state, first molecular excited state, second molecular excited state. So you get a new state forming due to the existence of an attractive exchange potential. And this new state kicks in, and when the normalized coupling strength gets strong enough, then the energy keeps on going down as the interaction strength gets stronger. So what we've got is a new state being introduced due to this exchange potential. And the energy of the state is dependent on the strength of the exchange potential. Now, if you take this bit of physics and you extend it to the many-site case, what you get is a distribution of state energies. And in the metal deuteride problem, then the idea is that you've got helium-4 and you've got deuterium. You've got these null reactions going on from site to site, and if the coupling's relatively weak, you generate a continuum of state slightly below the molecular state. This would give rise to neutron charged particle emission effects, sort of much more like Andre was talking about earlier. This model agreed with the Chamber and Cecil results quantitatively in terms of state energies coming from different host lattices. If you have moderate coupling, so the state extends down about 4.5 MeV, you actually can, since the compact states can exchange lattice rather efficiently, the deuterons can dump energy to go down to the proton plus triton channel. And you have a mechanism for making slow tritium, consistent with some of the results people have talked about today. If you're in the strong coupling, this is supposed to be strong coupling limit, then you have the possibility for the states to have energies that extend all the way from the molecular EE state energy down to the helium-4 state. And since all of these are able to exchange energies with the lattice easily, you have a ladder of a couple of phonons, actually roughly 20 phonons at a time, going up and down 24 MeV to make helium-4 and heat. As has been talked about before, helium-4 has been observed to be produced in quantitative measure with the excess energy to the nearest 10% experimental. The conclusion is that we're interpreting a Kasagi experiment that's measuring the compact DE states. The idea is when helium-4 dissociates, the deuterons are produced close together. They have trouble tunneling apart from one another. We've developed a coupled lattice and nuclear reaction model, call it the lattice resonating group method. Propose a new second-order other-site reaction mechanism. Been exploring models for many-site reaction processes. Mechanism for compact state formation is the dissociation of helium-4 and so forth. The bottom line is that you actually can get information from the Kasagi spectrum about what the range of compact state energies are. Because if they're spread all over the place, that's going to show up as a triangular dependence of the energy spectrum in a Kasagi experiment. The point is that these distributions are potentially observable.
The result that he cited.
I'm Pam Voss. My co-authors, Jack B. and Stan Schbach, regret that we could not come to Indianapolis to present this paper in person. However, we are thankful to present the paper in this manner. Our paper is entitled Thermal and Pressure Gradients in Polarized Palladium-Deuterium System. If you have any questions regarding the content of this paper, you can contact me. My email address is bossp@spaywar.navy.mil, and my fax number is area code 619-553-2836. Now, unlike most folks who, in conducting their experiments, they use palladium rods, wires, and foils. Our approach is different. What we do is we do palladium-deuterium co-deposition. And what we do is we take our electrode, nickel mesh, copper foil. We've also used copper, gold, and silver wires. We immerse them into a solution containing a palladium salt and a background electrolyte. And we put a current there and deposit the palladium metal in the presence of evolving deuterium gas. And you end up getting this cauliflower-like structure. It's black, it's mossy, has a lot of very high surface area. And because of this structure, we have non-uniform distribution in the current density and the overpotential. Because it's a very large surface area, we get rapid absorption of the deuterium into the metal lattice. And we also have achieved very high deuterium-palladium loadings. We've measured deuterium-palladium loadings greater than 1 And we achieve these loadings within seconds. Now, we have not done any calorimetry of the palladium deuterium system ourselves, but we do measure the temperature of the cathode and the solution temperature, and we've always have found that the temperature of the electrode is 2 to 3 degrees hotter than that of the solution, indicating to us that the heat source is the electrode and not Joule heating. While we have not done calorimetry, Mel Miles at Naval Air Warfare Center Weapons Division has done so. He has run 3 cells, and he has achieved excess power every time. His excess power ranges anywhere from 100 to 400 milliwatts. What we have done is we have done infrared imaging of the electrode during the co-deposition process. And in these experiments, we take a nickel mesh electrode, put it very close to the cell wall, and have imaged it using an IR camera. And here, if you look perpendicularly, you see the distribution of the hot spots. They are a very short time duration. If you view it from the parallel, you see the temperature gradient. The temperature gradient is very steep, telling us that the heat source is very intense and that it is located close to the contact surface. In one instance, we actually did get catastrophic melting. We had filled the cell before we left for the day. And the next morning when we came in, the cell contents had boiled away. And instead of getting the black, mossy palladium, we saw these silvery streaks of palladium along the cell walls. And when we took samples and sent them away for analysis, the metallurgist told us that the only time he had seen formations of this type was when metal had melted underwater. And palladium melts at 1,552 degrees C. Now, the infrared results indicate to us, or suggest to us, that the events we are seeing are explosive in nature. And if they're explosive in nature, you should see pressure waves. And the easiest way to detect pressure waves is to deposit your palladium and deuterium on a substrate that is pressure sensitive, such as a piezoelectric crystal. And that's exactly what we've done here. We have our piezoelectric substrate. It's a lead zirconium titanate disc of this radius and that thickness, and here's the source of it. And on it we have a silver electrode, and onto which we plate our palladium. And the idea is that when you get a heat source, you should get a pressure wave that would hit the piezoelectric crystal, and you would see a constriction of the crystal. And this would show up as a voltage response. And once the crystal relaxes and expands again, you'll see a relaxation curve. And this is a very reversible system, and the areas of these curves should be approximately the same. So here we set up our experiment. We have a Faraday cage. Inside it we have our electrochemical cell. This is our counter electrode. It's a platinum wire. This is our piezoelectric crystal. Here's the silver film exposed to the solution. The rest of the surface of the crystal we have covered with an insulating material. We have a potentiostat to control the voltage between, or the current between the counter electrode and the silver on the piezoelectric crystal. And then we have the leads from the piezoelectric crystal going to oscilloscope where we measure the voltage difference. And that voltage difference would be proportional to the constriction and expansion of the crystal. And here we see typical results. This is for low current cells where the current is less than 1 milliamp. This is the results for higher currents between 4 and 5 milliamps, and this is for zero current. And initially, we don't see anything going on, just some background noise. But eventually we get to a point where we have enough palladium on the silver where we start seeing these spikes. Here, at the higher currents, we see a lot more activity. At this point, we have evolving deuterium gas, which is going to be contributing to some of these features that we see. And interestingly enough, when you turn the current off, you still see these events occurring. And these events continue on for as long as 3 to 5 days after you've turned the cell current off. If we look closely at this example here we see a pressure gradient, which has caused constriction of the crystal. And as I said before, when the crystal relaxes back, the area of these two peaks should be the same. And you can clearly see that this area of this peak is going to be greater than this one. So there's another source contributing to that area, that peak area. And if you think about it, if you have a heat source causing pressure gradient, you're also going to have a temperature increase. And that temperature increase is going to cause the crystal to expand. And so we have both of these features contributing to this area. After we have conducted these experiments, we have taken the crystal, put it into a light-tight envelope. We've put a membrane, very thin membrane, over the crystal and taped it in place. And then on top of that, we've put photographic film. And we've allowed it to be exposed to the photographic film for 3 to 5 days. And afterwards, we have the film developed. And you can see here that we're getting radiation of some sort being emitted from the dark spots here. You can see the outline of the piezoelectric crystal, and you see these distinct spots occurring. We don't know quite yet what radiation we're getting. We don't know if it's regular light. We don't know if it's X-rays or what. We're doing ongoing experiments to determine what the radiation we're seeing. Another thing we're working on is, can we quantitate the results we obtain with our piezoelectric crystal? And in particular, can we say something about the location of the reaction sites as well as the strength of the heat source? And this is the model we're looking at. Here's our piezoelectric crystal. We are assuming that our heat source has a spherical volume of radius A. And we have our heat source, which radiates out, and you get this thermal wave as a function of R. And this is described by this equation shown here, where the temperature at any time R or any time T is dependent upon the magnitude of the heat source. K here is the heat conductivity of the palladium deuterium material. A, of course, is the radius of the initial sphere. And if you take as a limiting case A goes to 0, in this case it's a point source, this equation reduces down to this form here. Now, actual quantitative evaluation is going to be very difficult. You have to do a transducer calibration. We also have to do a temperature distribution, and the best way we can do that is by the IR imaging, so we'd have to redesign the experiment in order to do the plating on the piezoelectric crystal at the same time doing the IR imaging to get those, see where those spots are occurring. And we also have to make a number of assumptions. We have to make assumptions about the morphology of the co-deposited films as well as the heat transfer and the dissipation of that heat into the liquid phase. And clearly, the best chance that we have of getting any quantitative evaluation would be when we have a zero cell current, because we've totally simplified things then. We don't have evolving deuterium gas, and it would make things a lot simpler. And again, that work is still ongoing. So in conclusion, the characteristic features of the palladium deuterium system are that first off, you get immediate initiation of the Fleischmann-Pons effect. We don't have to charge our electrodes for weeks as other folks have to do with their rods and wires. Every time it works. We have great reproducibility and repeatability. We do see excess enthalpy generation at low cell currents, which is, again, opposite of what is observed with the rods and the wires. And we still see events at zero cell current. And these last two features indicate to us that you're going to have to revise our concepts, our theories on the nature of this phenomenon. We'd like to thank Dr. Frank Gordon for his support and Greg Anderson for his technical expertise in setting up these experiments. And again, if you have any questions, you can contact me at bossp@spaywar.navy.mil. My fax number again, area code 619-553-2836. Thank you.
Welcome to the American Physical Society meeting on cold fusion. This is the lecture on the impact of heavy water on nickel light water cold fusion systems. Previously, we have reported the observation of excess heat in nickel light water systems using a variety of nickel cathodes electrically polarized versus platinum and gold. The experiments used redundant data acquisition systems. 1 Hertz sampling times, and a variety of temperature probes. The configurations were used to provide large delta T's with long initial baselines. The calorimetry uses a static, low heat flow, multi-ring system with feedback temperature control. Both ohmic and metallic controls are used, along with noise power measurement thermal waveform reconstruction. The advantage of thermal waveform reconstruction is that the calorimeter is examined for its impulse response to prove it is linear and time invariant. In these group of experiments, we have also characterized the materials with 4-terminal electrical conductivity measurements, both before and after use in the system. The thermal power spectroscopy is based on using V times I as the electrical input power, and this creates a lower limit to the detected calculated heat. One advantage of noise measurement is that false positives can be ruled out when the system is driven by input electrical powers on the order of the noise level, as seen on the case in the left. Thermal spectroscopy has revealed the presence of optimal operating points in many cold fusion systems. This is important because there are only a narrow focus of functional input electrical power drive points. The height of the optical operating point manifold differs between samples and is time variant. In fact, it is found that with loading, the optimal operating points increase in height. Optimal operating points appear to be generalized behavior for cold fusion systems. They're important because the origin of the heat, that is, at which electrode it occurs, is correlated with the driving of the system with respect to the peak. In addition, the peak indicates a possible role of breakpoints in the power delivery curve. Knowledge of the optimal operating point system and the manifold can improve reproducibility and efficacy of cold fusion systems. In these experiments, the cathodes used were spiral, gas-free nickel, cold worked, which were set up against a platinum plate. Electrical resistivity of the electrodes were determined by 4-terminal conductivity measurement using an electric current source and a high input impedance electrometer. Geometric factors were determined by caliper. This figure is a thermal power spectrogram, which is shown as a vertical axis representing power in watts. It is a logarithmic scale. The horizontal axis is time. The left side of the figure is the baseline of the calorimeter, and it can be seen that the intrinsic noise level is on the order of somewhere between 8 and 100 milliwatts. In the dotted line segments, input electrical power and the observed detected output power as heat are shown. Shown are 2 levels of heavy water with the electrical joule control between them. The joule control used an electric resistor, and note that it detected exactly the input electrical power. This figure shows the rate of generation of excess heat in joules per second as a function of the heavy water doping from none to 7%. It can be seen that for increasing heavy water and for increasing power applied to the system, there is an increased rate of generation of excess energy. Looking from the point of view of the optimal operating point manifold, this figure shows the impact on power gain of increasing electrical power input. It can be seen that for all concentrations of heavy water dopants tested, there is a decrease in power gain as the input electrical power is increased. That is because we are on the right-hand side of the optimal operating point manifold, and here there is gas stream loss as we increase electrolysis in a wasteful way. Although small quantities of heavy water will increase the output of these systems, for larger amounts there is destruction of the nickel and a rapid fall-off of the power gain. This figure shows the impact of 15% heavy water upon these systems when they are driven above 700 milliwatts input electrical power. We are able to see from the excess energy point of view that the power gain falls precipitously from 2 to less than 1. The system loses all over unity performance. In addition, there is destruction of the nickel. By 4 terminal conductivity measurements, the resistivity falls from 8.8 microohm sonometer down to 8.0. We have used this as a test to determine inactive material in nickel. In conclusion, we report that heavy water can yield significant incremental increases in the observed excess heat for nickel light water systems when using gas-free, spiral-wound, cold work nickel cathodes. However, we have also found that there is a limitation to this, and that under the conditions of overdriving, that is, for heavy water concentrations greater than 4%, and for input electrical powers greater than 700 milliwatts into these devices, there accrue irreversible changes in the nickel, especially fast than 1 watt. We thank the American Physical Society for hosting this meeting, and Dr. Scott Chubb for chairing and organizing the meeting, and the members of Jet Energy Technology for helping and supporting this work. Thank you.
Welcome to New Energy Research Laboratory. I'm Gene Mallove, and we're very sorry, Ken Rowan and I, that we cannot attend the APS cold fusion session in Indianapolis. But we thought we'd give you a little cook's tour of the Sonofusion research that we're doing here. But before I mention that and show that, and Ken talks, I want to draw particular attention to the current issue of Science, which of course is dealing with bubble fusion of a different sort performed at Oak Ridge National Laboratory. No mention in there, of course, of continuing work for many years of Roger Stringham and cold fusion, Sonofusion. The very first cover of Infinite Energy had, in fact, a story on that topic. And then there were other issues of Infinite Energy, particularly number 19 and number 24, that discussed the matter of Sonofusion and how it might relate to cold fusion. I might say that Nobel laureate Julian Schwinger, in our issue 24, drew a connection between the phenomenon of sonoluminescence and cold fusion, dating back to his 1991 lecture at MIT. Without further ado, I'm going to turn over the scene to Ken Rowan, who is doing the bulk of the work here at New Energy Research Laboratory on Sonofusion. We're also helped by engineer Jan Roos, who does not appear in this video. Thank you.
Okay, I'm Ken Rowan, Laboratory Manager at New Energy Research Lab. I want to show you what we've been working with over the last year. Starting off with Roger Stringham's original reactor over here. We found that leaky seals and other problems made it unattractive for the demonstrator that we hope to commercialize when we get his process running the way he says it does. So we came up with a smaller reactor right here, which you can easily see piezoelectric elements at both ends of the stack mounted into a very compact stainless steel structure composed of these pieces here, as you see on the table, a hollow core, which then places these two piezoelectric stacks about 1/4 inch apart for a 2.5 inch cavity diameter. And both of these reactors are run with commercial crust electronics, ultrasonic electronics taken out of a jewelry cleaner. And we have applied that to one of our test benches right here, which is in semi-operation at the moment. We have a data acquisition system here, Hewlett-Packard Agilent system, operating their BenchLink software through a laptop computer, and you can see one set of display on the screen to get an idea of what the graphics looks like. And this is collecting data sampled at a period ranging from seconds to many minutes or up to an hour for each sample, and as long as you want. And a Seebeck envelope calorimeter to measure the heat evolved from the cell, and we happen to have this running at the moment. A nice hissing sound is from sine wave excitation coming from the signal generator and on the amplifier. We're presently running this at 40 kilohertz. You can see on the oscilloscope here we're operating nearly in phase. I can swing the frequency generator down a little bit, bring it more in phase, and you can hear that it's now starting to become a little more turbulent. And this is one of the things that we're researching here, what parameters affect the cavitation that we're looking for. And so far we've had just a few events of excess heat, but virtually none of them repeatable. So it's been hard for us to hang our hat saying that we have positive results. And most of them, like what you see on the screen here, have been no. So we're trying to find out what is going on and what isn't. And our work continues. Here we go. We have some artifacts of prior exposures, including the titanium foil, which Roger Stringham claims to be one of the active metals. And our present piezoelectric structure is constructed with a titanium disc, which we're using directly as the exposed material substrate for it. You can see the erosion patterns on there if the light isn't reflecting too badly off the surface. We've also saved water samples from most of our runs over the last year, and due to recent events, we will be bringing some tritium measurement equipment, liquid scintillation equipment into here to analyze the samples that we've saved, and maybe we have had something that we haven't known about. And presently we also have reactors, one reactor with Michael McCoubrey at SRI International. He's presently trying to look for helium with our apparatus. With the recent events in the Science article that has caught our attention lately, I wish to focus on some of the issues that pertain to our work here at New Energy Research Lab and to the science phenomenon in general. And to make it concise, I have it written here sort of like a mini lecture. So we'll make the best of our time here. The recent publicity about the science article on sonofusion re-exposes the dynamics of the scientific method as it is actually practiced and the problems which have surfaced in the cold fusion debate. The scientific method, like logic and mathematics, is a supposedly perfect and impeccable tool for gaining knowledge. The scientific method cannot be practiced in its sterile purity. It must be implemented by human beings who have faults and limitations. These faults and limitations get in the way of the execution of the scientific method, and this interference is being ignored. Compounding this basic state of affairs is the loss of awareness that experimental evidence is the foundation of science. Theory is merely its superstructure. Experimental evidence states what is true, what exists. Theory allows us to predict what else exists and gives meaningful direction to research. When experimental evidence conflicts with theory, theory must give way to the physical data. Max Planck, the founder of quantum mechanics, once said, "We have no right to assume that any physical laws exist, or if they have existed up to now, that they will continue to exist in a similar manner." What he meant is that our understanding of the principles which govern the physical universe are susceptible to change. He recognized the human factor in science. Laws are actually nothing more than models of understanding. The cold fusion dynamic can be understood within this awareness. Another factor which helps to complete the picture is remembering that what we have called physical laws do not necessarily have universal application or absolute manifestation. Examples are in order. The first example is a perfect parallel to cold fusion. It is the history of electronics and semiconductors. 100 years ago, vacuum tubes were the predominant semiconductors in electronic circuits. Their performance was understood by plasma physics. The transistor came on the scene in 1947, and plasma physics could not explain it. Plasma physics does not have universal application. Solid-state physics was developed to explain the transistor and to guide research by predicting transistor capabilities. In those days, science was a social environment which allowed ideas to flow and to change. Today, that climate of awareness has changed. If the transistor were discovered today, it would be met with comments such as these. The transistor is a mistake. You made errors in your thinking and your measurements. Plasma physics says it cannot do what you claim it can do. The electrons won't flow freely enough at room temperature. You cannot gate electrons with only half a volt. It must be 50 volts or more. Where are the high voltages? Where are the high temperatures? Where's the heat dissipation? Your claim that it conducts not only electrons but also electron holes is ludicrous. You're off your rocker. Vacuum tubes only conduct in one direction, and you claim some transistors conduct in both directions. Don't you know that plasma physics forbids this? You can't possibly have a semiconductor. This is pseudoscience. And so their comments might go. Another example drives home the fallacy of the universality or absoluteness of a law. No one would argue that gravity is sometimes present and sometimes not. It seems to be a universal and absolute manifestation, that it is always there. No one would ever say that a piece of metal will not be drawn towards the earth. Now add the effect of another physical principle, Venturi effect, and a chunk of metal can be made to move away from the earth, an apparent violation of gravity, yet we all know that airplanes and helicopters fly. Likewise, hot air balloons fly, using yet another principle, buoyancy, to overcome the effect of gravity. Our simplistic understandings of physical laws get us in trouble by predicting wrong outcomes. Once again, experimental evidence prevails and we modify our theories by realizing that one physical principle can modify the manifestation of another principle, even to the point of negating it, as in the rising balloon. With this in mind, it is folly to demand that the principles of plasma physics always manifest. The difficulty of designing good experimental protocol is an example of this ubiquitous interaction of physical principles. Getting a single principle to manifest purely is extremely difficult. The history of scientific developments and the complex interaction of physical laws shows that there is room for astonishing claims of cold fusion. Claims of impossibility and non-existence are unscientific for another reason. It is illogical to claim that something is impossible or does not exist. In order for impossibility or non-existence to be true, all conditions must be known in order to identify that the cited condition does not exist. This requires omniscience. It is safe to say that omniscience is not a human trait. Likewise, a negative claim cannot be proven, and a negative conclusion is not universal, because all it takes to make either of them false is the introduction of another condition, another premise. The freezing of water illustrates this point. If we conclude that water cannot be liquid with the conditions that 1, the water is pure, and 2, that the temperature is below 0 degrees Celsius, the truth seems to be stated. Add a third condition of high pressure, and the negative conclusion that water cannot be liquid becomes false. Be careful when you state that something does not exist or that something is impossible. By our human nature, all conditions may not be known. The severe criticism being given cold fusion that it is not real and its research is unscientific is itself unscientific. With this said, we at Cold Fusion Technology, Incorporated, are justified in our pursuit of evidence that Sonofusion is real. We are doing good science, following the scientific method with open minds. We fearlessly press on, knowing very well that our human faults and limitations interfere with our work. Clinging to the truth, whatever it is, instead of to our favorite theories and beliefs, will ultimately lead us to where we want to go, to arrive at an ever more accurate understanding of our physical universe.
Thank you, Ken. I might just add, in the background, with that camera jar, that we do have in mind to prepare a number of demonstration units, and this just shows that we're getting ready to do that if we find that the excess heat that we've seen sporadically and questionably on occasion ever gets stabilized. Thank you for listening.